Hello everyone, my name is Leonardo Banchi from the University of Florence, Firenze, in Italy. Here I'll talk about the problem of generalization in supervised quantum classification using tools from quantum information theory. The bulk of my presentation is based on the following paper that is available on the archive, and you can open it with the shown QR code. The problem we studied is as follows. So we want to learn how to classify states that depend on some external parameters x. We do this, as in supervised learning, by using a training set made of t pairs, where each pair consists of a state rho xt for some particular choice of the parameters that we call xt, and the corresponding class that we call ct. Supervised quantum classification is different from quantum state discrimination and hypothesis testing, though these are related. Here, the main task is not to perfectly recover the true class for the states in the training set, but rather to build a classifier that is able to generalize well, namely assign the correct class even to unseen input states not belonging to the training set. So the study of generalization is basically the most important aspect in machine learning. It is what makes machine learning different from a mere optimization problem. The main result of my talk is twofold. So we formalize quantum machine learning, in particular supervised quantum classifiers, using tools from quantum information theory such as state discrimination, entropic quantities, data processing, and so forth. The main technical result is a bound on the generalization error, namely the out-of-sample classification error, that depends on the Renyi mutual information between the classical parameter space X and the Hilbert space Q, where the quantum states rho of X live, as shown in this equation here. As we expect, this equation shows that the generalization error basically goes to zero when the size of the training set goes to infinity. Before going on with the theory, let me clarify what are the main differences between the problem I've described and quantum state discrimination. In quantum state discrimination, the states appear with some known probability distribution P of x, or P of x and c if we also have the class. Then, optimal discrimination strategies can be analytically constructed using either Hellstrom measurements for binary classification problems, while suboptimal choices for multi-class problems are also obtained via pretty good or square root measurements. The main difference in machine learning is that, on the other hand, the probability P is unknown. So we just have some correctly classified samples, and we need to build our classifier using just this partial knowledge. Then, is our classifier able to generalize? Is it also able to classify previously unseen data? So this is the main question. Now, before introducing the formalism, let me also show some possible example applications of our formalism. So, as a first example, we can define a binary classification problem to check whether some states are entangled or not. Suppose you have a machine, for instance, that outputs quantum states rho x depending on some tunable external parameters that we call x. An experimentalist, suppose that an experimentalist was able to perfectly characterize what happens for some particular values of x and see whether the resulting states are entangled or not. Based on their experience with the above states, the experimentalist now builds a classifier. So the question is then, how good is this classifier with the new values of x? Another possible example application is for quantum channel discrimination, which is a very general topic with many applications in quantum information theory. So consider the following example. So imagine that we have a self-driving car which is enhanced with quantum sensors. So quantum light, possibly entangled quantum light, is used to screen the outside world, and this light will be partially scattered and reflected, but some photons will go back to the detector camera inside the car. So the state detected by the car depends on the objects living in the physical world, that here are called X, and the task is to make decisions based on those objects, like stop the car, turn left, or turn right. So now, this quantum self-driving car may seem something incredibly complex, but there are related proposals that have been experimentally tested, such as quantum illumination and quantum radars, where quantum light was shown to provide an advantage for target detection. Quantum light can also provide advantages for barcode decoding and pattern recognition, as we have shown in this recent series of papers. So here, in the papers shown here in the bottom left corner. So here, each physical barcode is read using quantum light, and the different colors in the barcode physically correspond to different quantum channels that scatter light in a different way, for instance, using different wavelengths. So in these papers, we did show that the physical pattern recognition tasks, such as using light to perform handwriting recognition, is significantly simpler than decoding a barcode, because errors are tolerated. So for instance, a human eye is able to instantly recognize all the characters on the right, even when some pixels are randomly flipped, as in these pictures here. So we were able to formally justify this intuition by showing that the lowest possible training error depends on the fidelity between the two states that describe either white or black pixels, as shown in this equation here, but to the power of the minimum Hamming distance between images from different classes. So the minimum number of pixels that you have to flip in order to turn a number 4, into, for instance, a number 9. And for the MNIST dataset, a popular dataset, this is about 30. So because of these powers, so the error is much smaller. So practical classification can also be done by optimizing over the operations performed by the detector, for instance by optical circuit, and then followed by some classical post-processing of the quantum measurement results. In our paper, we used convolutional neural network for the latter task. Another example, which is quite popular these days, is to use a quantum machine to classify classical data. This is done by first embedding the input data X for instance images using a parametric quantum circuit like the one shown in the figure B. Then the next step is to measure the loaded data into a quantum computer with a POVM, generalized measurement, and get the class C of X from the measurement outcome. So in the literature, this POVM is typically performed via Naimark dilation, that is with a tunable quantum circuit followed by a projective measurement on a suitably large ancillary system. Another example is for many-body physics. So in the first paper here, the authors proposed the problem of quantum phase recognition and used the quantum version of convolutional neural networks for the optimal discrimination or suboptimal discrimination. So the task there was to decide the phase of a many-body system depending on some external parameters like magnetic field strengths, which play the role of what we call the parameters X. Another related problem discussed in this paper below was to use machine learning to estimate the entanglement negativity in many-body quantum states from the measurement of a few observables. And these observables were the moments of the partially transposed density matrix. So we showed that these moments can be measured using copies and swap measurements. So the central idea of that paper was that the observation was based on the observation that knowledge of the first moments is typically enough to predict all the others, and hence the entanglement via the negativity. So let's now jump to the results. I have shown that our formalism is quite general and can be used to describe many different physical scenarios. Let's now formalize the problem more mathematically. Remember that we have a training set made of t correctly classified pairs, and we can build a classifier from these pairs and numerically check generalization by studying the classification error with the testing set. So the testing set is basically similar to the training set, but with different pairs. And these pairs were unseen during training, so they are completely new for the model. To fix the notation, we call quantum embedding the mapping from X to rho of X, although in general we simply have a parametric states, and we can perform classification using a P of M as described above. So the big question is, what can we expect? What kind of training error or testing error can we get? So let's define a loss or cost function in order to quantify this error. So for a fixed P of n, the probability to get the class C for a state rho xk in the training set is given by the trace expression in the first equation. So the training error is basically the sum over all probabilities to get the wrong outcome, namely to get the outcome C, which is different from the true value ck that is known in the training set. And this is then averaged over all the elements from the training set. Then to study whether the model generalizes, so we have to introduce the abstract average loss, which is a kind of the real classification error. So why I call this abstract? Well, because we don't know the data distribution, so we don't know the probability P, so we only have some independent samples from the training and the testing sets. Now, the abstract classification error is the one typically employed in quantum state discrimination, where the optimal P of M's are well characterized. So here, on the other hand, for a fixed embedding, the optimal measurement to minimize the training error can be obtained from empirical risk minimization and can be analytically computed, for instance, using Hellstrom measurements for binary classification tasks. And this optimal measurement that minimizes the empirical, so the training error, is what I call here pi of capital T, where the dependence on capital T, which is the training set, reminds us that it is constructed indeed from the training set. I can also do the same with the abstract classification error and construct the optimal measurements that I call pi star. So this pi star is the true optimal measurement, but we will never be able to find it simply because we don't know the distribution P. So in this language, then the testing error is the one written in the last equation, and it is basically the empirical loss over the testing set, which is T prime, capital T prime, when we use the P of M, P capital T, that was constructed from the training set. So this loss is a single-shot linear loss, but later on I will discuss what happens with multiple shots. So when we use multiple copies of the states to perform the discrimination task and the classification task. Okay, so let's now study generalization as a function of this quantum embedding, so of these parametric quantum states. So you will see this picture many times to summarize what I'm talking about. We can expect that with whatever notion of complexity, the classification error, so this red curve, should decrease with more complex models. So the training error then basically shows the same trend of this red curve. So with more complex models, for instance, more parameters, training error is normally lower. Then the theoretical minimum error that can be achieved by any statistical argument is called the bias risk, and is the one showed here with the dashed line. And this, of course, the theoretical minimum lower error. So the difference between the red curve and the bias risk is what is called the approximation error, capital A. So if you have an infinite amount of training data and an arbitrarily complex model, this is the error you may expect. But on the other hand, the average testing error, which is the light blue curve, is basically the average loss with the classifier built from data, namely from the training set. It cannot be smaller than the classification error, and the difference between the light blue and the red curves, which is what I call G capital T here, is the generalization error, which clearly depends on the training set. So this studies how the data-driven classifier performs with unseen data. The behavior of the training and testing errors in the previous picture follow from the bias-variance trade-off from classical statistics. So consider here, for instance, the plot in the top left corner. And so we may, where we have a bunch of data, and so we may consider the very complex model which perfectly interpolates all the data, but this may have a very high variance and overfit the data. So we can also choose a trivial constant model, which will have a high bias and underfit the data, of course. And the best classical model, according to this classical bias-variance trade-off, is indeed a trade-off like the one shown in the third picture on the top. And these three regimes can be explained using the curve like the one I've shown before. So we won't study here what happens in the deep learning-like regimes, where models with a very, very high complexity can have both low training and testing error, although this is for me a very interesting topic for future research. So in this slide, now I summarize what are the main results of our theoretical analysis. So we have shown that the generalization error is bounded by this B quantity divided by the number of training samples, while the approximation error depends on the properties of the average encoding states, namely the ones defined below. So both the quantities entering in the generalization and approximation errors can be expressed using entropies, as we can see from the equations in the right below the figure. So the B quantity entering in the generalization bound depends on the Renyi-Chu mutual information between the quantum embedding and the classical input space, while the approximation error, even for multi-class problems, depends on the mutual information between the quantum embedding and the class space. So the entropies that enter in the generalization and approximation errors are defined for this classical quantum state, where C and X are classical variables, while Q refers to the quantum embedding. So I won't show the proof of what are these main results, but you can check the paper for all the details. So here I just want to say that our generalization bound has been obtained by combining, I think in a new way, results from Rademacher complexity from statistical learning theory, then operator inequalities and operator monotones, and in particular the following lemma, which is new to the best of my knowledge. So this lemma states that the average one norm of some operator is upper bounded by this quantity in the equation A12. And this is an operator version of the standard generalized mean inequality that is shown for arbitrary values of A and smaller than B in the last equation. On the other hand, the approximation bound is obtained using more standard results, like again, the Hellstrom theorem, the mean entropy and mean mutual information and entropic inequalities. Most of these inequalities are discussed, for instance, in this paper by Koenig and others. While on the other hand, the definition and some of the properties of the Renyi mutual information that appears in our generalization bound are discussed in this paper by Berta and others. Okay, let's see what kind of conclusions we can get. So the first one is that good embeddings should maximize the mutual information between the class space and the embedding space and minimize the mutual information between X and Q. So basically, good embeddings should compress the input space X, throwing away all the information from X, which is unnecessary to predict the class. So this intuition is similar to how the information bottleneck principle works, and we will see more detail later on. So let's consider now two extreme cases where we get somehow two extreme results. So in the first one, different inputs X are mapped into different orthogonal vectors in the Hilbert space. So basically, in this case, so this X and Q are the same. So for this choice, the approximation error is minimum, but the generalization error is maximum. So this encoding corresponds to what we will get in the far right of this picture shown here. On the other hand, we also have the trivial constant embedding. So this embedding has no information at all about either X and C. So this trivial choice has maximum approximation error, but minimum generalization error. So in the picture here, we are basically in the left side of the picture. So large approximation, small generalization error. So far we have only considered the single-shot linear loss. We can now discuss also a many-shot version of our loss function, where the discrimination strategy now uses n copies of the state, like in the second equation on the left. So in the asymptotic limit, we were able to show that the approximation error decreases exponentially with the maximum fidelity between different states. So namely the quantity shown on the equation on the top right. So this is compatible with the fact that higher complexity, in this case higher Hilbert space, so bigger Hilbert spaces imply smaller training error. But on the other hand, we don't have yet a full understanding of the asymptotic of the generalization bound. So we conjecture that depending on the embedding and also on the data distribution, so the B quantity increases either polynomially or exponentially. So again, this is consistent with the fact that the generalization error should increase with very complex models. And of course, understanding whether and when the increase is just polynomial would be very important for applications. So our conjecture is based on the behavior of the classical mutual information within observations, which displays indeed this Q regime. And this mutual information can be obtained as a lower bound on this B quantity, on the logarithm of the B quantity to be precise. Okay, let's now focus on some applications of our theory. So we first check the prediction that bigger Hilbert spaces have lower approximation error, but typically larger generalization error. So we have performed a simple numerical experiment where data of two different classes, C0 or C1, are Gaussian distributed. So we use a simple embedding called angle encoding, extended by taking n copies. So we have then numerically shown that the approximation error exponentially decreases with n, while the generalization error increases with n more slowly, as shown in this picture where the number of qubits n is shown within each circle. So this is consistent indeed with our theory. As another application of our theory, we can formally prove some intuitive results, and for instance that low-dimensional embeddings and low-entropy datasets generalize well. And more precisely, for good generalization, the embedding Hilbert space does not have to be necessarily small, but the most important point is that rho of X should scramble the information in X in a small subspace of the full Hilbert space. This is kind of intuitive, and it was also conjectured in this paper by Lloyd and others, though a formal proof was lacking to the best of my knowledge. So in our analysis, this was formally proven via some inequalities that link our quantities from generalization bounds to the fidelity between different quantum states. The conclusion is that good embedding should cluster data from the same class into nearby points in the Hilbert space and separate as much as possible different points from different classes, as in this picture with the three classes, red, green, and yellow, shown here. So, however, due to the trade-off between approximation and generalization, so this ideal picture cannot be really achieved, as we will see also in some numerical examples. Another recent result that will appear on arXiv in an updated version of our manuscript is that the link with kernel theory. So for pure state embeddings, we show that the generalization bound can also be expressed as the trace of the square root of the normalized kernel operator. So this links our bounds to kernel methods, which are used in quantum support vector machines and in quantum enhanced feature spaces. So according to our theory, the worst generalization is obtained when the kernel matrix is close to an identity matrix, something which is quite likely with large dimensional embeddings. So when using quantum kernel methods, the one conclusion is that one should avoid kernels that are close to an identity. So there is another interesting conclusion from our theory, that namely to favor generalization, the final Hilbert space must be small, but the initial one can be big. So what we can do is that we may iteratively discard information via pooling layers, for instance, as in quantum convolutional neural networks discussed in this paper here. So one can prove via data processing inequalities using our entropic bounds that pooling favors generalization but harms the accuracy. So if it is possible to achieve low training error with pooling layers, then generalization can only be better. So finally, I also show how our results are linked to the information bottleneck principle. So this is an information theoretic framework to study machine learning and deep learning. So this is based on the idea that learning algorithms should squeeze as much information as possible about the input, keeping only the relevant information to predict the class. So quantum information bottleneck principles were previously discussed in these papers at the bottom, but for different applications. So in our problem of classifying classical data, so for a particular problem of classifying classical data, we can treat the quantum embedding rho of x as a bottleneck, and the optimal embedding according to the information bottleneck principle is the one that minimizes the following Lagrangian for a particular value of beta. So beta here allows us to explore the trade-off between approximation and generalization. So we found that the solutions to the information bottleneck Lagrangian can be written as a kind of self-consistent equation that can be solved by iteration. From our numerical experiments, we see that embeddings constructed by solving the above equation for low beta have large risk or loss, but small generalization error, while for large beta, the embedding shows low average loss close the theoretical minimum value given by the bias risk, but larger generalization error. We can also see this geometrically as well in the block sphere, and you see that for moderate values of beta, the embedding starts to cluster the data close to each other, but without separating the different classes, which here are the red and yellow points. On the other hand, for large beta, the data are clustered and well separated, although there are still points in the brown cluster. And this cannot be removed since the bias risk is non-zero for this particular choice. Okay, so we have introduced quantities from quantum information to study generalization in supervised quantum classification. We have studied how the Hilbert space dimension, pooling layers, but also the amount of noise that I haven't discussed affect the approximation and generalization capabilities of quantum classifiers built from data. So this is all summarized in this picture on the left. So there are many open questions. So the main one for the long term is to understand what happens with models of extremely high complexity, to see whether there is a sort of deep learning transition after which more complexity is also good for generalization. Other open questions deal with the study of different cost functions, and I don't expect our results to be too much affected by the choice of the cost function, as we basically get the same results via the information bottleneck principle, which is kind of cost function independent. But this is a topic that is of course worth exploring more formally. Another interesting future direction is to formally also clarify what happens in the asymptotic regime with multiple shots. So with this, I conclude, and I thank you all for your attention.